So let's start with this theorem right here, theorem 2.6, which is in the section about Newton's method. Try to understand what the theorem says, first of all. So we're starting with a function that's in C2AB. I did say what that meant, I think, the other day. Anybody remember what that's called? Twice continuously differentiable. It means not only do the first and second derivatives of f exist, but they're also continuous functions. You can actually have derivatives existing without being continuous. There are some wild examples out there of derivatives that exist everywhere, but are not continuous functions. They're pretty weird, but they do exist. So it's nicer to assume they are continuous, though even continuous functions, I will show you, maybe not today, can be pretty wild as well. But they do satisfy certain properties that discontinuous functions do not satisfy. Anyway, effectively, f is a nice function, functions that you're used to from pre-calculus and calculus. If p is a point in AB, the interval, that's the open interval from A to B, that's a root of f of p equals 0, and whose derivative at p is non-zero. So think about this geometrically. That means the slope of f as you go through the root there is non-zero. You've got a non-zero slope. You have a slanted crossing of the x-axis when you graph it. Then there exists a number delta, possibly very small. In analysis, epsilon and delta are often thought of as being small numbers, but it doesn't have to necessarily be small, such that Newton's method generates a sequence converging to p, the root of f, for any initial approximation p sub 0 in this possibly very small interval. It is possible delta could be very small, like 10 to the negative 100 or something. Not usually that small, but in theory, it's possible it could be very, very small. All right. So we're going to try to understand the proof, but we're also going to draw a picture here to help us understand. We've got our function f that we're trying to approximate the root of. Let's draw A over here and B over here. F is not only continuous, but twice continuously differentiable. Basically, you draw some nice smooth graph, it's going to be twice continuously differentiable. It could have a lot of oscillations in it. It could cross the axis more than once, but let's just say it crosses the axis once right there. There is our root, our 0 of f, this nice function defined on this closed interval from A to B. F of p is 0, and I have also drawn it so that f prime of p, the slope of the tangent line at this point, is non-zero as well. Let's pretend that's the tangent line right there. I also happen to draw it so that it looks like that's an inflection point. That's not typical. Not typical to have an inflection point at a root, but that's the way I drew it, I guess. So the tangent line ends up on both sides of the graph. Not a typical thing, but that's the way I drew it. There exists a number delta, possibly very small. So again, that if your initial approximation of the root, p0, is in the small interval, then the sequence generated by Newton's method converges to p. In this picture, can you say what delta is? Not really. You can't really just look at this picture and say what delta is. Delta could be big. It could be this entire distance, say from P to A there. It's possible. It's not clear what delta will be until you actually look at the proof. And even then, it still may not be clear. But remember, before we go on and look at the proof, that with Newton's method, you are generating a sequence via this other function g. G of x is x minus f of x divided by f prime of x. And we saw last time that when you graph g, it's going to have a fixed point at the same place f has a root. Okay, so, well, you know, usually your y equals x line should be drawn at a 45-degree angle if the scales on the axes are the same. But if I do that, I'm going to go off the paper here. So let me draw y equals x at not a 45-degree angle, which if the scales on your axes are different, it very well could look like it's not 45 degrees. At this exact same spot P, G is going to have a fixed point. So the graph of G is going to cross that line right there, what will the graph of G look like? Well, the one we saw had in the example from last time looked about like this. And we also saw it happened to have a slope of 0 at P. So maybe the graph of G, at least near F, looks about like that. Actually, I'm wondering, I don't remember from the proof or not, but I'm wondering if the delta is determined by trying to avoid where f prime of x equals 0. So you're not dividing by 0. I do see, it looks like in this picture that f prime could be, well, if not 0, very close to 0 there, which actually means the graph of G is going to go up high, maybe right about there. Certainly 0 there and 0 there. If f prime happens to be 0 right there, the delta probably needs to be smaller than this distance right there, is probably what happens. And again, the graph of G would go up and probably have some sort of vertical asymptote there because you're dividing by f prime of x there. Okay, I'm not going to worry about that, just a verbal comment. We did see again, you got a fixed point there at P, and we saw, at least in the example from class last time, that the slope of G was 0 there at that fixed point. And that we will see is what ultimately makes this convergence typically pretty fast. Again, you generate the sequence by defining Pn to be G of Pn minus 1. So P1 is G of P0, G2 is G of P1, etc. The theorem says, start close enough to P, this is going to converge to P. All right, let's try to understand the proof. Right away, we got the function G. So the proof is based on analyzing Newton's method as a functional iteration scheme, just like I've been saying here, where Pn equals G of Pn minus 1 and G of x is this function. We've been talking about this. Let K be between 0 and 1. Why do you think they're using the letter K there? Where do we see K before in other theorems? We got to think about other theorems here as well. We were talking about functional iteration. We were wondering, when is a fixed point stable? Or when we think about the contraction mapping theorem. If the derivative of G in absolute value was always bounded by some number K between 0 and 1, that was a condition under which the contraction mapping theorem said you had a unique fixed point. G had a unique fixed point. Perhaps that's what's going to be going on here, is that's going to be a value of K where G prime will be less than K. But wait a minute, how do you know G prime is going to be less than K in absolute value? It doesn't look like it would necessarily be small, close to 0. Well, let's read on. Sometimes you have guesses about things, but you're not sure. They're telling you what to do. If we first want to find an interval, possibly very small, that G maps into itself. Oh yeah, that's like the fixed point theorem, right? Map the interval into itself. They're probably going to apply that here. For which, yes, my thought about K is right. For which the absolute value of G prime is always less than or equal to K on this small interval. Again, it's not clear that this is possible. The author is hinting that it's going to be possible, and now we have to see how it works out. So what are the details of how it works out? Since f prime is continuous, how do you know f prime is continuous? It's part of the assumption of the theorem. In fact, we know f double prime is continuous. F prime itself for sure would be continuous. And since f prime of P is non-zero, that's part of the assumption as well. Part A of a certain exercise implies blah, 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 blah. Oh, here's where it starts to get really hard. I mean, you can look at that exercise, but does what it's saying here make sense? What are they saying? So the f prime's continuous function, it's nice. Its derivative value at P is non-zero. There exists a delta 1, just some small positive number. So the derivative is always non-zero, is what this is saying in this interval. So that we avoid dividing by 0. Thus, G is defining continuous on this interval. We're not dividing by 0. X is continuous, f of x is continuous, f prime is continuous. G will be continuous as long as you don't divide by 0. So we're trying to avoid dividing by 0 here is the goal. But how do you know this works? Well, when your function is continuous, I mean, I don't have the graph of f prime here. Let's just pretend we've got the graph of f prime. You know, near P, its values are going to be positive and maybe oscillating a bit. This might be what the graph of f prime looks like near P. Its value at P is non-zero, and I've drawn it to be positive. Since it's continuous, it's got to be positive in value near P. There's no way it can jump down to a negative value, like right away, as soon as you increase away from P, because that would be a discontinuity. I mean, maybe it could get close to 0 pretty quickly. Maybe it looks more like this. But because of the continuity, that's why there's some number, delta 1, so that if you're between P minus delta and P plus delta, or delta 1, I guess, the outputs of f prime are still away from 0. They're still not equal to 0. It's the continuity. That should be intuitive. Proving that's not super easy. You got to go back to more the definition of continuity to prove that. It was an exercise. That's what they're saying. An exercise, when I've taught real analysis, I've assigned that kind of exercise before. I don't know if ALK does or not. So drawing, even though we're not proving that, drawing a picture like this can help this make sense. What's the next thing to do? Well, we're trying to show G prime satisfies this property, so we better find G prime. Differentiate G. Use this formula. Use the derivative of f. Well, the derivative of x is 1, so we get a 1. And they're a quotient, I guess. I need the quotient rule. Low d high minus high d low over the square of what's below. So it's just quotient rule there. Saying it simplifies to that, that's just algebra. Get a common denominator of f prime of x squared. 1 would become f prime of x squared over f prime of x squared. I'm not dividing by 0 on this interval, so there's no problem with dividing by 0 here. You combine the fractions, the numerators would cancel. The numerator of this one would cancel with, because of the minus sign there, with this part of the numerator. And the minus sign with that minus sign makes a plus sign. So you get this. This is the derivative of G in terms of f, f prime, and f double prime, when G is defined to be the function you iterate for Newton's method. Okay, kind of interesting, possibly useful. So yeah, that's going to be true on this interval. And since f is in C2, G will be in C1. F is twice continuously differentiable. First and second derivatives exist and are continuous. G is once continuously differentiable. Its derivative exists and is continuous. Notice its derivative involves the second derivative of f, which we know is continuous. But we don't know f triple prime is continuous. So finding G double prime probably would involve f triple prime. We don't know that's continuous, so we can't say G is C2. Is that a big deal? No, it's good enough to be C1. It's kind of weird, you know, C2, C1. When you write these kinds of theorems and you make these kinds of assumptions, what you're trying to do is you're trying to keep your assumptions minimal to still see under which conditions the theorem is true. You know, why not do a C3 or a C4 or a C5 there? Because you don't need to, that's why. It's good enough for f to be twice continuously differentiable. You don't need it to be thrice continuously differentiable. Right, thrice meaning 3 times. You don't need it. If it were thrice continuously differentiable, f triple prime existing and being continuous, then it would also be twice continuously differentiable. But you don't need to make that assumption, so don't. That's why theorems are written in the way that they are. You're just hoping all this stuff is good enough. We are assuming P is a root of f. So in fact, it's a root of G prime. Hey, that's the confirmation of the fact we saw at the end of class on Tuesday, the fact that the derivative of G at the fixed point at the root of f is 0. P, the root of f, is a fixed point of G. Right, G of P equals P minus f of P over f prime of P, but f of P is 0. This is P minus 0 is P. P is a fixed point of G, but what we're just seeing in this proof is that it also has a derivative equal to 0 there. And that is what makes the convergence for Newton's method extra fast. At least under these conditions, f prime is non-zero. We're also going to see today that if f prime of P is 0, that's more difficult to deal with. So what do we have now? So this is 0. G prime's continuous and equal to 0 at P. So if you change the input of G prime a little bit away from P, the output of G prime should still be close to 0. It's kind of similar to this picture, except here we were trying to avoid being close to 0 with G prime of P is 0. But by continuity of G prime, if you move a little bit away from P, it may not equal 0 anymore, but it'll still be close to 0. It won't go too far away. And that's where you get the K. K is not a specific number because we don't have specific functions here. But there's got to be some number K where this is true by continuity. It's okay we don't know what K is. We don't know what K is because we don't know what F is, we don't know what G is. But by abstract properties of continuity in this case, we can still say this is true. There's got to be some such K. Could we say K is bigger than 1 as well? Yeah, you could also say K is bigger than 1, but we want it to be less than 1 so that we can apply that contraction mapping theorem. We want to set this up so we can apply the contraction mapping theorem ultimately. What's delta? Delta is just some number possibly less than delta 1. You can always get away with a smaller delta. That's what they do here. And this must be the delta in the conclusion of the theorem. So we're set up now to use the contraction mapping theorem. Almost. We've got the derivative bounded by some small positive constant. But the contraction mapping theorem said the G also has to map the interval into itself. And that's what's left to do before we can actually apply the contraction mapping theorem. It remains to show G maps this interval into itself. In other words, if the input is in the interval, then the output's in the interval. If X is in this interval, then G of X must be in the interval. Mean value theorem is now applied. There's some number C, my favorite Greek letter, between X and P. You don't, by the way, you don't know whether X is bigger than P or less than P. Could be either. So we just say between. Where the absolute value of G of X minus G of P is the absolute value of G prime of C times the absolute value of X minus P. Now, that equality there is not technically what you see in the conclusion of the mean value theorem. In the context of this situation, you would see it as G prime of C equals G of X minus G of P over X minus P. But then take the absolute value of everything and rearrange. And you'll get this equality there. Right? You did this kind of thing in one of your homework problems where you were applying it in this kind of way. Now we do this line, and here, this is the key line that makes everything work. We're trying to show, what are we trying to show again? We're trying to show if X is within delta units of P on a number line. That's what this means. It's between P minus delta and P plus delta. That the output G of X is also within delta units of P. So that's why we look at the absolute value of G of X minus P. That would represent the distance between G of X and P. Why is it equal to that? Somebody tell me, why are these two things equal? P is assumed to be a fixed point of G. That's why they're equal. Or it was proved to be a fixed point of G. Then this quality is from the mean value theorem. Then this inequality is from what we just did on the previous page. And then K is less than 1, so this is less than that. But X is in the interval there, so this is less than delta, therefore this is less than delta, done. X is in the interval, this is true, therefore G of X is in the interval. G maps the interval into itself. Now apply the fixed point theorem, the contraction mapping theorem, really, to say that, well, okay, yeah. It's just the interval gets mapped into itself. You could say it's a unique fixed points because it is the contraction mapping theorem. But they just say it converges to P. Actually, it was more beyond the contraction mapping theorem. It was talking about when this kind of iteration generates a sequence that converges to the fixed point. All right, so that proves that Newton's method works under these conditions and works well, though your initial guess might have to be really close to the true answer. Section 2.4 is full of theorems as well. We first need to fully understand everything, this idea of order of convergence. Suppose a sequence Pn converges to P, but is never equal to P. Each Pn is not equal to P. Just to keep things simple. It's not that you can't have sequences that are sometimes equal to what they converge to. It's just simpler to think of the typical example here where they don't equal P. If positive constants lambda and alpha, and it is important that they're positive here, and meaning non-zero, exist where this limit is true, then we say the sequence converges to P of order alpha with asymptotic error constant lambda. Now that's kind of a difficult thing to wrap your mind around here. One way to wrap your mind around it a little bit is certainly with examples, and the next page has got some examples. Homework problems will have an example or two where you're thinking about this. Excuse me. But it's also worthwhile to think of this in terms of an approximate equation. Saying that the limit as n goes to infinity of the absolute value of Pn plus 1 minus P divided by the absolute value of Pn minus P to the alpha power equals lambda. Saying that that limit is true is, well, basically equivalent to, in a vague kind of way, saying that this ratio is approximately equal to lambda when n is large. That's a very vague statement. So this is not something we're trying to prove here, but I hope it makes some intuitive sense, right? This is the way you think about limits with calculus students. You could also say more. You can also say it gets closer and closer to lambda, possibly with some deviations away, but generally speaking, gets closer and closer to lambda. I can make it as close as I like to lambda if n is sufficiently large. Another way to say that, if I multiply both sides of this approximate equation by Pn minus P absolute value to the alpha power, is that this approximate equation is true. The distance between Pn plus 1 and P is approximately lambda times the distance between Pn and P to the alpha power. Now we're assuming Pn approaches P here. We're assuming the sequence Pn converges to P. So therefore, these distances here definitely go to 0 as n gets large. They get small, certainly less than 1 in absolute value when n is large enough. Remember, like, think about if alpha is big here. big meaning bigger than 1, 2, 3, 4, 5, 6, etc. If Pn is really close to P, so that this distance is close to 0, you raise a number close to 0 to a large positive power, it's going to be even closer to 0. Now, lambda could be big, but even if it were big, as long as alpha is big, this number is going to be fairly small when Pn is really close to P. And so what you're saying is effectively the distance between the next iterate and the true answer, the true fixed point of G or root of F, is effectively smaller than the distance between Pn and P. And the bigger alpha is, the smaller this is. It's the way to think about this intuitively. When alpha is 1, that corresponds to what's called linear convergence. Linear convergence. When alpha is 2, it corresponds to something called quadratic convergence. Called linear convergence and quadratic convergence essentially because it's the powers of this thing here, the 1 and the 2. Quadratic convergence certainly is faster than linear convergence, and that's good. We want fast methods. However, linear convergence is not that slow, to tell you the truth in the big scheme of things. It's just that quadratic convergence is much, much faster. Book's got an example here. It's an example where they don't actually specify what the sequences are. They just say, pretend these limits are true. Notice this one, the absolute value Pn has a power of 1, and this one, the absolute value of Pn tilde has a power of 2. That's linear convergence, that's quadratic convergence. And the goal here is to look at this table and say, hey, quadratic convergence to 0 is much faster than linear convergence to 0. Certainly much faster. I mean, look at those exponents, those negative exponents. It's not that this is slow in the usual sense of slow in math. I mean, essentially, we're approaching 0 with our approximations getting cut in half every time, which you could call exponential decay if you wanted to. But for numerical methods, it's still not typically thought of as being as fast as we might like, as what we would get typically with Newton's method, for example. And quadratic convergence, that's more like it. There, it's almost like you're doubling the exponents, the negative exponents there. Okay, so just to give you a little feel for that, what's the big point of what comes after this in this chapter, section 2.4? The point is that in most typical situations, Newton's method does converge quadratically, which is good. That's the big overall point, theme. There are some special situations, however, where it doesn't work so well. And we want to look at both of those situations. In those special situations where it doesn't work so well, besides the ones that you looked at in the project, where it blew up because you were dividing by 0 or whatever, or maybe it was chaotic behavior. Besides those kinds of situations, there is another kind of situation where it doesn't work as well as you might hope. But let's look at these theorems now. Okay, our first theorem is at the bottom of the same page here. Take a breath, trying to wrestle with these theorems as well now. What do we have here? Let G be C of AB, just continuous. Why just continuous? Because it's enough to prove the theorem, that's why. There's no power of the C, that just means it's continuous. If it were C1, then it would be continuously differentiable. If it were C2, it would be twice continuously differentiable. Just a plain C means just continuous. G of X is in AB for all X and AB, so G is mapping the interval from A to B to itself. Suppose G prime is continuous on the open interval, and that a positive constant less than 1 exists where this is true. So again, the wheels in your mind should start turning, saying, oh, I guess this would be a situation where the contraction mapping theorem would hold. if G prime of P is non-zero, which is not what typically happens with Newton's method, right? This is not Newton's method typical situation, because with Newton's method, we got G prime of P was zero typically, it seems, unless it's undefined. As long as F prime was non-zero, G prime of P was zero. So this is actually not something that applies to Newton's method. It's applying more generally to arbitrary iterations, like the logistic map. If the sequence converges to the fixed point, it's only linearly. Not quadratically. And that's what we kind of observe with the logistic map typically, is if it did converge to the fixed point, it wasn't super fast. And sometimes it was fairly slow. Right? And G prime at the fixed point, if it was between -1 and 1, the fixed point was attracting. And if G prime's a nice function, that means if your initial condition, your seed is close to the fixed point, it will converge to it. That's the kind of situation we're thinking about here with this theorem. There's convergence only linearly. Looking at the proof here, we know from the fixed point theorem that the sequence does converge to P. Why? Because G maps A to B into itself. The fact that G prime was always less than or equal to K in absolute value means it's a unique fixed point. It's got to converge to the unique fixed point, not some other fixed point. G prime exists on the interval. It doesn't say G prime is continuous. Yeah, it just says it exists. No, it does say G prime is continuous. Okay. But here they're just saying it's continuous because existence is enough to apply the mean value theorem to G to say that for any n, this equation is true. The mean value theorem application is right there. That second equality. This first equality, well, Pn plus 1 equals G of Pn because we're iterating G, and P equals G of P because P is a fixed point of G. There's the application of mean value theorem. So we're effectively applying the mean value theorem here infinitely many times, once for each value of n. Where Cn is between Pn and P. Where are we trying to go with this again? Look back a page if you need to. We're trying to converge show it's only linear convergence. We're trying to show this limit is true when alpha is 1. And evidently not true when alpha is 2. Actually, the book doesn't really show it's not true when alpha is 2, but I think we can add to the book here. So they're trying to focus on this limit. That's their goal when alpha is 1. So they got to think about that ratio, evidently, in the end. Is that what they do? Yeah, looks like it. Right there, we were sort of looking ahead to the end of the proof here. That's okay to do. That can help you understand the proof if you know where you're headed. Track with me here. This is fun for people who like abstract math, which is not everybody. Not every math major likes abstract math, maybe. Even if you like abstract math, it doesn't mean it's easy, right? Or it doesn't mean it's, well, okay, it's worthwhile. We're trying to get to there. What's the argument in between? Pn converges to P, so Cn also converges to P. Why? Because for each n, Cn is between Pn and P. Here's P, and your Pn's are going toward P, maybe bouncing back and forth. Each Cn is between Pn and P. It's like a squeeze theorem kind of thing. They're going to be forced to go to P as well. Since G prime is continuous on the interval, this limit's true. Okay, this is just something new, perhaps, to think about this kind of thing right here. Essentially, this is the definition of continuity. You might remember from calculus, maybe, that essentially f is continuous at a point P essentially means the limit as x approaches P of f of x equals f of P. Maybe I shouldn't have used a P. P is not necessarily a fixed point or a zero of f here. Why do I say essentially this is the definition of continuity? Because there's some technicalities I should really add here, like f needs to be defined in some interval near P, that kind of thing. The limit of the function is the function value. That when you do calculus limit calculations in calculus, think about the definition of the derivative. When you're doing limit calculations, you're doing some algebra. If you're in math lab and you're helping the calc students, they've done this recently. You're doing the limits of something, and you're trying to do some algebra to ultimately cancel the h in the bottom of the fraction, so you can plug in h equals 0. It's at the end that you're using the continuity, and you can plug in h equals 0. That's what you're doing in essentially saying this is what continuity means. That's kind of similar here, except it's a Cn, and n is going to infinity here. Cn is kind of like the variable x. In the definition of continuity, x is approaching P. Here, it's a sequence, Cn. You're letting n go to infinity, but Cn is approaching P. So yeah, this is essentially the definition of continuity with some caveats. It's really something you have to prove based on that definition. So that must be relevant here. Where's it relevant? I guess it's right there. Limit as n goes to infinity of this fraction equals that. Well, okay, that's related to this equation here. Just divide this equation on both sides by Pn minus P. And to get from here to here, you essentially just take absolute values, and this is valid as well. So this is now fitting that definition of order alpha with alpha equal to 1, where this is the lambda right there. And it is important that this is non-zero, because that was part of the definition of order alpha convergence. The alpha and lambda are both, in fact, positive constants, non-zero. So that's like the lambda, and the alpha is 1. So it's converging linearly. The theorem statement says, though, only linearly, and they don't really prove that if it converges linearly, then it doesn't converge quadratically or with alpha to bigger than 1. But I hope that's somewhat intuitive. If you made this an alpha squared on the bottom, for example, or I don't mean alpha squared, if you made alpha equal to 2, if you made this thing squared, it's really like you're thinking about this limit. And this one's converging to alpha, or to the absolute value of g prime of P in the proof. This one, however, is going to converge to infinity. So it's diverging, because you're dividing by something going to 0. Goes to infinity. Meaning the entire limit really must be going to infinity. When I write equals infinity, I'm not implying infinity is a number here. I'm saying it diverges, grows without bound here. The only way such a thing like this would converge to something positive and not infinity would be if this thing was converging to 0 sufficiently fast. But it's not converging to 0, it's converging to this, which is non-zero. There's not really a proof, but just an intuitive argument why it does not converge quadratically. Theorem 2.9, and the discussion that follows is probably the most important part of this section. Gets even more complicated, though. Take a breath. How much time we have left? 28 minutes. Hang on. Let P be a solution of this equation, x equals g of x, so P is a fixed point of G. Suppose G prime of P is 0. That's the situation with Newton's method. With the G function, G of x equals x minus f of x over f prime of x for Newton's method. This is going to apply to Newton's method at least if G double prime is continuous and less than some number m on an open interval containing P. G double prime, the concavity doesn't get too big. They're not saying G prime double prime of P is 0. They're just saying G double prime doesn't get too big if we are close to P. Again, not today, but maybe next Tuesday, I'll show you even continuous functions can have some pretty wild graphs. Display kind of wild properties. So these kind of assumptions are not nothing to make. Most functions that we encounter in calculus and so forth are sort of so ordinary, we're so used to them behaving in such tame ways that we're not used to what are called wild functions. Dr. Wetzel always said call them wild functions. Some mathematicians call them schizophrenic functions, but it's probably better call them wild functions. They behave in wild ways. What's the conclusion here? Then there exists a delta, another one of these deltas, possibly a very small number, so that if you start in the small interval and you generate your sequence, it converges at least quadratically to P, at least quadratically, maybe even faster. That's what it's saying. And this inequality is true. Think about this intuitively. Then if you divided both sides of this inequality by the absolute value of Pn minus P squared, you'd get something somewhat similar to the order of convergence definition, wouldn't you? Where the m over 2 would be like the lambda. It's not a limit fact here, it's an inequality, but it's kind of related to the limit fact. Okay, so get quadratic convergence, really fast convergence, and this inequality is true. And this inequality perhaps could help us figure out error bounds, perhaps, possibly. I think we're not going to do that today, but possibly that could do that. Here's the proof where you need to apply Taylor's theorem that I suggested that you read briefly before class, which is really a generalization of the mean value theorem. Well, let's get going here. The start of it's similar. Choose K in the interval from 0 to 1 and delta so that on the interval, this is true. And G double prime is continuous. Why could we say all this? Again, G prime of P is 0. If G double prime is continuous, so will G prime be continuous. So if the interval is small enough, G prime is not going to get too far away from 0 is what this is saying. And we also want to be just in a region where G double prime is continuous for some reason. The reason's not clear yet. Next sentence is the argument from another proof shows that the terms of the sequence are contained in the interval. It was the first proof we looked at today. We won't go through the details of that. I'll let you think about that if you want. Okay, here we get to the most important part. Expanding G of x in a linear Taylor polynomial gives this equation. You're not used to writing this kind of thing when you think about Taylor polynomials or Taylor series. It's this part that would be the Taylor series of degree 1, Taylor polynomial, I should say, that would approximate G of x near P. But there's an equal sign there, not an approximately equal to sign. To get an equal sign, Taylor's theorem says you have to add on a term like this, where C, just like in the mean value theorem, is between x and P. P is the fixed point of G. P is a solution of that equation, so it's a fixed point of G. G prime of P also happens to be 0. X, what's X? X is any number between P minus delta and P plus delta. But when you write this equation, you want to imagine X is fixed, but arbitrary. C does depend on what X is. Now, they don't put the dependence of C on X in this notation, but I believe they do back in chapter 1. Let's look quickly to chapter 1. If I remember correctly. The dependence of C on X in this theorem here is in this remainder term in this equation, where the remainder term looks like this, and you see the C does depend on X there. C depends on X. C is really a function of X. I'm not saying in saying what I just did that you understand what this is talking about. But I am emphasizing C does depend on X. So they're hiding that in this notation. They're not being explicit about it, but it does. Going back to our proof here. The C right there does depend on X. It lies between X and P. P is fixed, but I could change X, so I'd get a different C if I change X. What are we assuming? Can this be simplified? Yeah, we're assuming P is a fixed point of G, so G of P is P. I can replace G of P with P, like that. And G prime of P is 0. I can get rid of that linear term, so I just get a more simple equation here. If we had time, we're running low on time. If we had time, what I would do is I'd consider an example to help you understand this a bit better. Maybe let G of X be cosine of X. And so P would be its fixed point, which we saw was like 0.739 or so. And maybe let X be 0.5 and see if you could estimate C. Maybe just graphically. Catch what I'm trying to say to do? That would be a worthwhile thing for you to do after class. Pretend G is cosine of X. Well, okay, it wouldn't satisfy that condition though. Maybe pretend G is the function we got from applying Newton's method at the end of class on Tuesday. We made the graphs on Mathematica. Maybe do that example. And let X be some specific number and see if you can graphically approximate what the C is to help you believe this and help it give it more meaning. We just don't have time for that here in class. In particular, when X equals Pn, replace X with Pn, you can say this kind of thing. Where we're putting a subscript on the C as well, just to emphasize it does depend on n. Pn plus 1 ultimately equals this. And so if you subtract P from both sides, you get this. Why are they subtracting P from both sides? Well, because it's part of the conclusion of the theorem is to do that kind of thing. And we'll need to do it to do the at least quadratic convergence part. And yeah, oh, look at the right side. Pn minus P squared. Divide both sides by that effectively and take absolute values. Now you're seeing the quadratic convergence where the lambda is this. I mean, there's some more arguments to give to get to this conclusion. We need to confirm Pn converges to P. That's part of the condition of the definition of quadratic convergence. And we also need the fact that Cn converges to P to say this. So I can replace the Cn there with a P there. But yeah, effectively, we proved quadratic convergence in this. And G double prime doesn't get too big. What's important that the lambda was positive here? Okay, now I see where they're going. This result implies it's quadratically convergent if G double prime of P is non-zero, so the lambda is positive. But they're not excluding the possibility that G double prime is 0 at P. Evidently, it's higher order convergence in that case, though they don't really prove that. Alpha could be 3 or 4 or 5 or 2.5 or something like that. G double prime is continuous and its absolute value is bounded by m. So I can get to this inequality, effectively replacing the absolute value of G double prime of P with m. We're not using this at the moment, not today at least, but maybe we can next Tuesday a little bit. Down to 18 minutes. What's worth doing here for the rest of class? Let's keep going. I'm not going to go through this part in detail, other than to just tell you, if you didn't read it yet, that what the authors are trying to do here is they're trying to derive Newton's method based on desiring quadratic convergence, based on trying to use the theorem we were just looking at, coming up with a g function whose derivative at p was 0. That's the heart of what they're trying to do there. I won't go into details.